I'm Steve Jones, and this is the Introduction to High Performance Computing. Now, I'm very excited that we have so many people signing up for this course. I've been watching enrollment for some of the other classes. So I think we're at 70 right now. That's a big number. You know, it's very exciting to me. So it means that there are a lot of people here who may be interested in HPC, or you want to learn about building a compute cluster. Maybe it's some of the software tools that you're interested in, or maybe it's the machine learning project at the end. We'll find out as we go. Or maybe you just think the class is an easy A, you know, so you signed up. All right, so here we go. So the overview of the class is that this first week today, we're going to discuss I'll give the introduction to the course, but we're also going to discuss your first course project, which will include the build of an HPC cluster. Everyone's going to visit the machine room and have the opportunity to put together a compute cluster from bare metal. So you're going to install the operating system and all the associated software. And even connect it together, power it in, plug in Ethernet, all of those types of things. So I think that's kind of fun. It may be the only opportunity you ever have to go into a server room. So that's kind of exciting. At least I think that is. That's the highlight of the course. The following classes, so then next week we have somebody from Victor Lee from Intel is coming in and giving the introduction to parallelism concepts. So you'll learn what parallel computing actually is, how to program, how to distribute tasks, those types of things. Then we move right into compilers, and we'll be using the Intel compilers, of course, in this class. And then we start moving into some of the performance analysis, profiling, MPI, the message passing interface, and then on to Python, and then finishing up with a tutorial on machine learning that's presented by Ashwin Mishra. He's a postdoctoral researcher. I don't see Ashwin here today. So that's our final course project that we have. So there's not an actual final in this class or midterm. We have two main projects and then a lot of homework assignments, quizzes, and things like that. So who's here? So myself, of course, I'm the director of the HPC Center. And then I'm also a research scientist in flow physics and computational engineering. And I see some other people from FPC here as well. And then we have our TAs, CAs, and then instructors. I think Karthik, who is one of the TAs, is out sick today. Jay Patel is here. He's one of the TAs, and you'll meet him in office hours. Jerry is up in the top there. Jerry just is a recent graduate, and he's staying on through the summer to help us out with the course. And Eric, I don't see Eric here right now. And then Ashwin, of course, I'm not sure Ashwin's here. So then we have quite a few people from Intel that are participating in this. Either they've provided support or they're some of the instructors that are in the class. And then we have you, the students. So there's quite a mix of people here. I was looking through the registration, and we have some people that are high school students that are in the summer visitor program. Undergrads, matriculated undergrads that are Stanford students, and then masters and PhD students. And then I think we have a handful who've snuck in of like postdoctoral researchers and others who weren't able to enroll for the class that are here auditing. I think auditing is not allowed during the summer session for undergrads, but some of the postdoctoral researchers are here as well. And so there are also people here from quite a number of departments on campus. So aeroastro, physics, bio, chemie, and others, computer science, EE. So we have quite a mix of people that are in the room. So I would suggest to everyone to meet the people that are here. There could be people in this class that are already using high-performance computing in their research or in their work. You may meet them while you're doing your cluster project and building the system, or just as you're going through the class. So if you really have an interest in this area, reach out, meet some of the other people in the class. So what to expect each week. So today you'll have some, well, sometime between now and Monday, we'll post some assignments up on Canvas. So they will consist of many or some of these things. They could be some pre-reading that you're going to do to prepare for next week's lecture, or video tutorials, could be one or the other. And they also could consist of some type of task to execute on the cluster, of one of the class compute clusters, where you will actually log on, compile some code, and run it, and generate some type of output. And usually it's to make sure that you have a good understanding of the lecture that you're about to attend. We want to make sure that you get the most out of each lecture. So each week, of course, is a new topic and a different person that will be giving the lecture. This week is the HPC cluster build that we'll be going over. Then we have quite a few weeks on the tools of HPC. And when I say tools, those include anything from MPI libraries to compilers to performance profilers, analyzers, different types of tools that will be in those following weeks. And then at the end, of course, the machine learning project. So homework assignments, pretty light, fairly easy. They'll all be cluster related. You'll always be logging on to the compute cluster, performing some type of task, and you'll have some type of quiz that will ask questions related to that task or something that took place in class. Some of them you may just be able to Google and get the answers. All the assignments will be posted on Canvas. Everybody knows what Canvas is? You know how to access? Yes? Okay. All right. Everything can be completed from your laptop, so you'll be connecting to the compute cluster, and we'll go over that in a few minutes here. Or if you don't have a laptop or you're unable to connect to the compute clusters, you can go to office hours, and we have a number of laptops that are available there, and you can complete all the exercises during office hours. Expect about a 2-hour a week commitment in either watching tutorials or doing homework or completing exercises. All right, so grading. Course projects, there are 2 course projects that are worth 30% of your grade, 15% each. Homework, another 30%, and that will just be the quizzes that we're grading. And then class participation, that just means like showing up. And I don't think we're taking attendance today, but we'll probably pass around a sheet, something like that. Jay will come up with some method for figuring out whether or not you're here. But we want you to show up. So, I mean, if you're just here for the A, you know, whatever, that's great. But I would much rather have you show up and you want to actually learn and participate and use the resources and you know, take benefit of the time that everyone's spending to come and give the lecture. So that's essentially it. So we have the course project there outlined, and then also the machine learning or deep learning project. All right. So TA office hours, they will be held in the CTR building, or Center for Turbulence Research. That's on the other side of campus. So you know, we are right here in Shri Ram, and it's all the way over here. The bookstore is right here, just to give you an idea of where it is. So it's downstairs. You'll go over there, and there's a small courtyard in front of it, and like right here's a spot where you can just go downstairs and into the conference room. That's where the laptops will be. Any questions about homework, quizzes, those types of things, you'll go there. The other set of hours we have are in our research and teaching lab. That's in Murrell, the Murrell building, or Mechanical Engineering Research Laboratory. And that is just down the street from CTR. So CTR is like right here, Murrell is right here. That's on the first floor, room 124. That's where you will go to complete your course project, where you'll go in there, plug together your cluster, get it up and running, then you can access it remotely for the rest of the week. So each group that is going to go there will have essentially a 1-week window to complete your course project. The first one starts this Monday, so it's Monday 10 a.m. That's when the first hours are for that location. So it's Monday 10 a.m. through Sunday midnight. is essentially the window of time that you'll have to complete the project. It should only take about 2 hours to do it. Could take up to 10, depends on how many mistakes you make. So we've had a number of students in our group that couldn't complete the project. We've been going through it again and again, just fine-tuning everything. But we have it down to where most of it is just copy-paste, when you're putting in commands. Just make sure you put them in order and don't forget a command or you'll get in trouble very quickly. All right, so resources for 344. Again, discussions, assignments, quizzes, everything is on Canvas. We have projects, any project files, sample code, course-related data. We'll announce where it is and how to check it out. It's on GitHub, but we'll include instructions each time on how you check it out and how you move it around and manipulate data. So I'm not sure if I mentioned in the slides anywhere, on the prerequisites, we don't have any prerequisite for you to know how to program in C. It's helpful, but you don't have to know how to program or even really use the command line too much. We provide sample code for all of the exercises. A lot of it will just be the tools that we're introducing you to. And you'll run the code. There might be some extra credits or bonus things along the way where you can write or compile your own things, and you're also open to run and do anything you want. We're not too concerned about that. If you want to try out some of your own code on there or do something, as long as you're not interfering too much with everyone else, and we'll let you know, or we'll just kill your jobs or whatever. You can try out different things. That's another great thing about this class, is that you have access to this very cool new hardware. There are people in our groups that are waiting for access to this, and I told them, no, sorry, you have to wait until the class is over. So you're the first people to access this system, which is kind of cool. So we have this main HPC cluster where you'll conduct all of your coursework on, and that's KNL is the name of the cluster, or Knight's Landing, named after the processor architecture. And then it has a very high-speed interconnect on it, the 100 gig interconnect, OmniPath, or OPA, it's named. And then we have the project clusters where you'll build and complete your project. We have 5 of those. So 5 groups will go to the machine room each week. And each one of those is a 4-node compute cluster. And then during office hours, we have about 30 laptops or so, I think, available. But I don't think we'll have that many people visiting office hours at one time. But there's plenty of laptops available there, and where you can complete your work. So connecting to the clusters. This is something that's very important. If you're going to be using your own laptop to connect, this is the #1 issue you're going to be working out in the next week if you haven't already. You need to have, #1, VPN client installed on your computer. There are instructions at vpn.stanford.edu. If you haven't set this up yet, you'll need your SUNET ID, of course, to access. Everyone has one. So install the VPN client. There's instructions for Mac, Linux, Windows on how to take care of that. You'll also need a terminal session or console, something where you can connect to the cluster via command line. If you're on Windows, again, ess.stanford.edu, they have Secure CRT and Secure FX available there. In order to run some of the exercises, you'll also need an X server. So Xming is one that's available. You can go to either one of those locations. Oh, these slides will also be available online, in addition to the session being recorded. So you can go to one of these locations and get your software for Windows. If you're using Mac, you're halfway there because the console client is already on your computer. You just need to get Xquartz to be able to complete the X session. So that's like an X redirection section or session where you can have the application running remotely on the computer but view it on your laptop. So Xming is something you'll need to install. If you're on Linux, no further comment is necessary. You have everything you need. But how many people have Linux installed? Excellent, good. Yeah, yeah. You guys are all set. Everything will just be through your terminal session or console session. So essentially the way that it works is you'll start up your VPN client and then launch whatever terminal session that you have, and you will just SSH using your SUNET ID, that's your authentication, SUNET ID at the login node, which is KNL-login. We'll have your account set up, I think, sometime in the next day or so where you'll be able to access the cluster. And we'll post that information on Canvas along with your first exercise that you're going to run on the cluster. I've mentioned HPC a few times, just a very high level of what HPC is. Essentially what it is an aggregation of computing power that provides more power than you would typically have like with your desktop or your laptop. So we even have some HPC systems where we label them as HPC, where they could be a single system. We have one from IBM where it has 2 terabytes of memory on just one computer. We still consider that an HPC system, a high-performance computing system, just because the amount of memory, the amount of processors that are available on it, but still just a single computer. And that computer, just to give you an idea of price of a system like that, I think is close to $300,000 for that one computer, all because of the memory. But it could be that that could be an example of thing, or it could be a collection of computers like that. But essentially, an HPC system has all the same elements that you would have on your laptop or desktop: processors, memory, hard drive, operating system of some sort, and they're usually just connected together by some type of interconnect or network. Could be Ethernet, could be InfiniBand, could be OmniPath. There's some type of network that's connecting them together. In the case of our course cluster, that's Ethernet and OmniPath connecting them together. One for setup of the system, the other for communication when you're running a job. So the course cluster that we have, this is where you'll be completing your work. So here we have a login node. This is where you SSH into. And in front of that, we have a load balancer. So the load balancer just automatically distributes you to one of these nodes based on load. So we've set this up and configured this in advance. So you'll just be automatically sent to one of these nodes right here. Each one of these nodes has a nice landing processor. So the nice landing processor has 272 cores. If you're interested in like core count, some of your laptops may have like 4 core or 8 cores. So 272 core per node. And some large amount of memory. I don't remember exactly what it is, maybe 100 gigs or so. And so once you're on the login nodes, you'll connect to compute nodes through a resource manager or a batch processing system of some sort. And so this is where we have just showing the layout, the Ethernet network, the OmniPath network that connect and plug everything together there. So you can see this over in the machine room as well. So we have this set up next to the machines where you're going to be doing your projects. So some of the ways you might use HPC at Stanford. The way that we usually see new users that come to us with a problem that they want to run on the system is they usually have a MATLAB problem. They're like, hey, I've got this MATLAB problem. I don't have enough memory on my computer. Do you have something where I can access and run either a set of jobs or just one job with greater access to memory? And so we have systems that have hundreds of gigs of memory where they come and run. Another way you may access an HPC resource here is just like in a class like this. So we use HPC as part of this class, but there are also quite a few courses on campus that use it as well, and we support those classes. They could be in CS or in ME or a number of other locations. I think there's one other class we're providing support to this summer. You may use it as part of a research group. There are a number of researchers in here that I can look around and see that are using HPC. And they'll use it in a number of ways. Either they'll have an application that is available from a company that has been written. Could be like a computational fluid dynamics application that is offered as a commercial product. And they just essentially do the physics, and the application takes care of everything on the back end for them, all the parallelization of it, and distributing data to the compute nodes. Something like Fluent or Ansys might be a good example of something like that. There could be an open source application. Maybe somebody has written something and they've made it available to the community. So that may take a little bit more work, to get that up and running. Or you may write your own application, and maybe some of the techniques you pick up today will help you in those efforts. So C, of course, writing your own application, that's where you'll get the greatest benefits of some of the concepts that you're introduced to in this course. So moving into our course project. Since this one's going to take quite a bit of work, this is what we're dedicating today to. So the first thing that you're going to be doing in the course project is connecting together a bunch of hardware. So we have the Stanford network that we have, where you'll be connecting to. And the first thing you'll do is connect your master node or computer to the network through an Ethernet cable. And from there, the master node connects to an Ethernet switch, again by another Ethernet cable. So we have the public network out here, or the Stanford network, where you can access anything you want, and the private network on this side, which you'll define in the configuration. And that's how you're going to access all of your compute nodes, where you're going to be doing any type of processing or other things there. And then from there, you're going to connect in all the compute nodes. So they'll connect into the private network switch. So it's pretty simple. I think everybody will make it through that part. The next part is you'll install the Linux operating system onto the master node. So that will be through I think we're using a DVD to install. So you'll just go through the basic steps of installing Linux. We have all the information in detail on how to do that. From there, you'll be installing the OpenHPC distribution. So this is a cluster management utility or collection of tools that have been put together to make it easier to build compute clusters. And once you've done that, you're going to create an image or a virtual system, that virtual file system on the master node, and that's what's going to be distributed out to the compute nodes. So the build of the compute nodes will just happen, magically, automatically, as you just start them up. And we'll go through that process here. And then you'll add some users and then submit a job to the nodes to execute and then turn in results to that. So that's just a high level of the project. Now to get into it in a little more detail. So we talked about OpenHPC just quickly there. So what that is a framework, and this is an open source framework that allows the automated installation of operating systems and software, or provisioning. That's a word you're going to hear a lot about, is provisioning of resources or provisioning of nodes. That essentially just means installing software. So OpenHPC is actually, underneath the covers is a tool called Werewolf. And this is what OpenHPC is based on. So Werewolf takes care of all of the node provisioning piece and software integration. And it's used to manage some fairly large HPC systems into the tens of thousands of nodes, could even be hundreds of thousands of nodes in there. It was developed at the labs at Lawrence Berkeley, actually by a good friend of mine. Greg Kurtzer was the developer of that. He also founded CentOS, if you're familiar with CentOS, the Linux operating system, and what's known as that today. So he's still over at the labs. He's working on a new project now. But what this is focused on is just the scalable system management or large system management when you're talking about hundreds of nodes. and being able to manage those, install, reinstall, monitor things, making sure things have disks that are working or processors that are reporting correctly or memory that's functioning, correctly. If you had a memory issue on some computer, you would want to know about that in advance of submitting some 10,000 core run on it, and having it run slow because of one failing node. And then also event notification, things like sending you email alerts, letting you know that there are problems with the system. And so all of this works in a modular plug-in style system where you're just installing everything into this image. And so that's what OpenHPC is. All right, so on installing CentOS, we'll just kind of go through this quickly. This is not very exciting or glamorous in any way, installing operating systems. But there are just some steps in here that you're going to be doing. There are going to be two interfaces that you're setting up on here. We provide all this data to you. The main ones you're going to be worried about are just where this X is entering in your cluster number. To make sure you're configuring it correctly. You don't want to configure your cluster as the same number as somebody else. That'll cause unforeseen problems for you and the other group. And then also the IP address too. You'll be entering that in. But there are just some simple details that you do in setting up the network interfaces. One to connect to the Stanford network, the other connecting to the private network. Pretty simple. And then the next piece you'll have is installing making a couple of selections in the setup. So you could set these up where they run in run level 3, which is basically just on the command line. But we're setting them up in run level 5, which means there will be a graphical user interface. That just makes it easier for you. In troubleshooting, it allows you to start up the system and have that nice GUI that you're probably used to on your Mac or Windows machine. And then you can launch a console session or a web page and look at instructions on how to continue. So there are just a couple of selections that you make in there. All right, so in the configuration of the master node, this is where we start getting into a lot of the options that you have for setting this up. We've set this in a way to where you don't have to edit files. And we've done that with Perl. So if we deconstruct like this Perl line, how many people know Perl in here? No one, okay. So that's fine because you don't have to do anything other than just copy this command and run it. But just deconstructing this really quick, this is just saying that we're doing a search and replace. We're searching for this instance and replacing it with that in this file. Very easy. So the first thing that happens here in the OpenHPC setup is they want us to disable the security measures. So we do that. We disable SE Linux, Security Enhanced Linux, and then you reboot the system. That'll take a few minutes. System comes back online, and then we're going to start doing some installation of software. First thing we do is we use Yum. Does anybody know what Yum stands for? I know what it is. Oh, what it is? Anybody know what it stands for? Yeah, that's what it is. I had to actually look it up today. I forgot what it stood for. Yellow Dog Update Manager. Anyway, so what it is a package manager. And when I say package, if you see right here, we have like RPM. That's Red Hat Package Manager. And what an RPM is a collection of scripts or software or code that are installed on the system. So say you want to install some software on a system, you can do all of the scripting that you have to do for it, and use a package manager to create an RPM, and then Yum reaches out to places like repositories, which are collections of packages. And so in here, the first thing we're doing after we install the operating system is we're saying to update any repositories that we have installed by default or we've pointed to on the system. So, and the -y is saying accept all or answer yes to everything that comes up. So first thing we do is we install CentOS, then we update CentOS to the latest version of every package that's available. The next thing we're doing is we're installing a new repository. And this repository is the OpenHPC repository. And then this is the version number of it and some other detail in there. Just deconstructing that is OpenHPC release number 1.3-1, and that's Enterprise Linux 7 and the x86-64 platform, just so you have an idea of that. That's probably information you'll never need to know again. And then after we do that, we're just doing a yum repo list, looking at repositories and making sure that everything's active. So from there, we start moving into provisioning pieces. So in order to set up the compute nodes on this project, you're going to have provisioning services enabled. And OpenHPC has the base provisioning pieces, and then also we mentioned Werewolf. This is where Werewolf gets installed onto the system. And then being able to do provisioning, we need to tell the master node on which interface or network connection to provide provisioning services. So here, we're just doing a quick edit, telling it to provide it on this interface, which is the private network, and it just writes it to that file. And then we're enabling the service that does provisioning on there. And so here's where we get into building the actual image or the operating system that's going to be distributed out to the compute nodes. So we do this in a chroot or a root environment, virtual environment that we've defined and we're building here. So we essentially create the installation of CentOS on this master node, and this is where we do all the definitions and setup of it. So it's essentially like a sandbox or a jail where we can manage that installation that is sent out to the compute nodes. So we go and we define the location of it. We make the location that's based on this environment variable here that we've exported. And then we do an install and update of CentOS. So this actually installs CentOS in that location. It goes out to the repositories and does a complete installation. Now this is a very lightweight install. I think the install of CentOS that's in this repository or in this image is only a few hundred megs. So it's very quick to install. It runs in memory on the computer. We don't run it on a hard drive. So everything is just run in memory on the compute nodes. And then the next piece I think we mentioned earlier is about the resource manager. This is how you access the compute nodes. This is another thing that we're installing. So we install OpenHPC and then the resource manager. Now they have lots of great key features that they advertise about what PBS does. All these automatic failover, like if a component fails or node fails, it will redistribute your job to a different node. And a nice health check framework, and it's free and open source and all that. But what does it really do? It allows you to request resources or compute nodes and send your jobs out to it, and then ensures that we have fair sharing of the resource. So if you have 200 people submitting jobs for just a few nodes, it makes sure that it just does it in a nice orderly fashion and has everything. Yes? Well, I'm not sure how they, so the question was, I think on Sherlock, about the allocation of resources or fair share of resources that exist on Sherlock. So the way that we do it on our systems is we have a number of different queues, and they have different restrictions. Like one may run for 24 hours. One may run for 72 hours, and another one is unlimited. And we have different nodes that are allocated to those. And then we run a fair share algorithm that looks at a 28-day window. And it looks at your utilization for the last 28 days, and then will run your jobs accordingly. So if you haven't run quite a bit, and there's a decay that's built in too, so it decays like 5% a day. So if you haven't been running a lot in the past 28 days and you go to submit a job or request nodes on the cluster, your job will move up the queue in front of everyone else's that have been running more often. And so I'm not sure what level of programming they've done with their schedule to make sure that people have fair use of resources. But you can define those things in the workload manager. And so that's where I spend a fair amount of time is working on that part of it, making sure that everybody has equal access. But there are ways to game the system too. And I usually don't point those out because then everybody's doing those things, and then you have to find a new way to restrict resources. So that's essentially it. And essentially the way here is the access flow to the cluster. So we look back here at the KNL cluster, and we have the login node. So users log in here, they submit jobs, and then it goes out to a work queue. And this is where you would have your restrictions or policies out here that would define on how people can access those resources. And so essentially what you do is you log into a login node, you create a job script, and then you submit that with a queue sub command, and that will go into a queue. And if there are resources available, it'll go out there and run on the nodes. If there are not resources available, it may sit there for some period of time waiting to run, depending on the restrictions or policies of that queue you've submitted it to. And so getting into the resource manager piece, this is another large part of the setup that you're going to be doing. And this is where we have seen a lot of issues come up in just our own testing of this course project. Because if these things aren't defined correctly, you won't be able to submit jobs and run and complete your work. So what takes place here is that the first thing we're doing is installing the package on the master node that enables PBS, or the resource manager that we're running here. And then not only do we have to install it, we have to just run some simple commands here to, number one, enable it. So every time we restart the computer, it starts up, and then we start it for this session as well. Then we add the compute nodes. These are the nodes that you'll be setting up. So you have to define each one. Now you can also have extended attributes. Maybe you have a compute node that has a GPU on it, or a compute node that has a large amount of memory. You can define those attributes here, and that will allow people to request those resources with some different flag. And then the configuration of the compute node. You have to do a very similar thing into your image or your chroot environment. So you're installing here, and now we have a yum command with this install root command. And that's saying to install that RPM over into the image versus just on your master node. So that's a way of doing redirection of installation of RPMs. And once we have that installed, then we have to edit a bunch of files that are out in that environment, also on the master node, and then also out in the virtual environment. And that's essentially just adding the host that's going to be handling the resource management. In this case, it's your master node. Sometimes it can be a separate node that's taking care of those things. And from there, we just enable the service. We don't start it because that's just a virtual image. It's not actually running. It's just waiting to be installed. So we talked about the provisioning process. And just to give you a very high-level detail of how this works, this is like, I think, just maybe 5 of the probably 40 operations that take place in here. But essentially what you're going to be doing is when you're doing the provisioning or building of your compute node, is you're going to remote power it on. You're going to send a command over to the management interface on the computer, which will just start it up. You don't have to be physically be there to do that. So you'll just connect to an out-of-band management port that will start this. And from there, the node starts up and does a DHCP request, or it does a request saying, hey, I'd like access to the network. And once the master node hears that on a port, it will have a number of communication sessions back and forth, and it will essentially say, oh, I know who you are. You've been defined in the database. I'm going to send you back CentOS and install that on you because that's what I've been told to do based on some commands that you've entered. So that's essentially how the compute nodes get set up. The master node is where you'll do most of the work. These ones, you just start them up and they automatically install everything. And the way they know to do that is because you've inserted them into a database. And by inserting them here, you've just said werewolf shell command, WWSH, add new compute node, here's the IP address, and here's the hardware address, or the Ethernet address, or MAC address, if you've heard any of those terms before. Those are the same types of ways you get onto the Stanford network using your hardware address. So you define everything in advance. We give you all of that data to enter. And then these are those management interfaces where we talked about, where you're connecting to and starting up the nodes. And so you add that all to the database, and then you define a provisioning image or provisioning set. And so here we're essentially saying, in this last screen we had the compute-1-1, 1-2, 1-3, 1-4. This time we're saying provision anything with the name compute-star CentOS 7.3, that's that VNFS we built earlier. And this is the bootstrap image we built earlier, and you're essentially saying anything with uname. If you run uname-r, that comes back with a boot version or kernel version. And then these are the files to sync to it. And that includes things like password group and shadow, which make up like your user accounts on a system. And then also some network detail, and there's some other things that we sync between the computers constantly. And once you've defined the computers to a provisioning set and told them what to boot to, we have the DHCP service, which is the one that answers requests when you're booting up the nodes, and we have a PXE update. That's the pre-execution boot. That's where it defines all of these items here on like how to start and what to deliver out to the compute nodes. Oh, yes. Mm-hmm. Oh yes, yeah, exactly. So, so we've defined everything, and then this is a point right here where we go and run the setup of it. But once it's set up, you can SSH right in or submit a job. Everything will just automatically happen. I mean, we're like almost to the end of the install here, and as the compute node starts up automatically, installs everything, and that usually just takes a matter of minutes. If we modified the boot process and all the BIOS boot options, we could have the startup just take place in a number of seconds versus minutes, but we haven't spent any time on these test clusters to do that. Yes?
So then in that case, how does PBS know whether to allow SSH jobs to happen or only jobs from the master to happen?
So we've... Sure, there are a number of things that we could define in either PBS or on the node to allow users to connect directly to it or not. And that's outside the scope of the class, but that's something you can define in both PBS and in the Werewolf configuration and on the node separately on whether or not you want to allow a user to SSH to the system. But in here, you can connect to the node either way. You can either SSH to it and run, or you can use the resource manager by just requesting, you can submit a job that will run in batch, or you can run interactive where you do like a Q sub dash capital I for interactive session. So there's 3 separate ways to access the nodes. So this is the last step in the provisioning piece, essentially is the start of the node. This is how you're going to tell the computer to start up remotely. And since the computers will most likely be on, we're just running a power cycle, but there are other options here. It could be power on, power off, reset, cold. I mean, there are a number of IPMI tool sessions that are available for this power option. Power cycle is the simplest. That's just saying cycle the power. And once the power is cycled, you can tail this file here that is the central collection point that you set up in some previous steps. I didn't show those here. So there are hundreds of commands here that are options and lines that we didn't include in this instruction setup that you'll be doing. And what we can do is we can just tail this file. And what you'll see in the setup process is that the first thing that's going to happen is that you'll have a compute node, like this B6 was one of the ones you defined earlier. We'll do a DHCP discover. It'll just start up and wake up and say, hey, where's the network? You know, does anybody know how to get an IP address? And that's the first thing that takes place. Then you will see an offer coming from the master node out saying, oh, yeah, I know who you are. You're on the database. This is the IP address I'm giving you. So there's the offer. And then there's an acknowledgement that comes back and says, okay, I've got this IP address. And there's a couple of other things that take place in there too. There's about 6 pieces back and forth communication with DHCP. We just have 3 of them defined. The next one, this is just another clip. You know, this is highly truncated here. But this is essentially saying that I'm giving you the kernel or your you know, base OS to be able to boot up. And then we distribute some of the data to it, the image that you've created, and then it gets to a point to where it reboots and then the system just goes into service. So these are some of the things that you'll see if you're tailing this file here. And once it gets to this reboot piece, that's about the point that you can go and log into like this one here, compute 1-1. So it's pretty simple. So after that, what you'll do is just some quick operations to set up your system so you can use your SUNET ID to log on rather than having a password on the system. So you just do a quick copy over of a file and run a quick update and sync time because if you don't have time synced, the time on the computer has to be within 15 seconds of the Kerberos authentication servers. If it's not, you won't be able to authenticate. So that's why we just update the times and have them sync with the same time server. Then you'll add your SUNET ID. So this is not your university number. It's like your SUNET ID, like mine is SM Jones. So you'll enter in everybody's SUNET ID in your group. Then you'll be able to log on to the systems. Now, to make sure you can log on to the compute nodes, you'll need to resync the files. So you'll resync the password, shadow, and group file out to the nodes. That'll allow you to authenticate to all those nodes. That should work. That's a push. We're pushing those changes out. Shouldn't be necessary, but sometimes if you have larger systems or communication traffic, you have to do a pull as well, where you're going and getting files. And this is just the expression you would use here to do it to all 4 of those nodes. Simple enough. That's pretty much it for the setup of the cluster and the course project. Again, I think it's going to be fun, you know, for you to be able to go and visit the machine room and do those things. So the things to do in the next week are number 1, installing the VPN client. How many people have done that already? Oh, only a handful. Okay. Make sure you get, oh, I think those are all people that are users, or most of them were. Current users. So make sure you have a working terminal client. If you need help with any of those things, come into office hours next Monday, and I'll be there. There'll be some other people, you know, that can give you a hand with that, or post on Canvas. Make sure you sign up for the class project. If you want to get it done quickly, go online on Canvas. There's a link to the Google Doc where you can add your name into the documents there. That's there. There's only 15 people per week. I think there's 70 in the class. So if you want to get it done quick, make sure to sign up. Otherwise, you'll be waiting weeks, you know, a week, 2 weeks, 3 weeks, whatever, until you are able to get access to the machine room. Make sure to watch Canvas for assignments, announcements. I think we'll be posting our pre-reading and exercises for next week's class, which is on parallelism. We'll post that in the next day or so. That's where you'll have information on how to access the course cluster. And then you'll be submitting a job and running some code on there. And then we might have a light quiz where you'll just enter in output from the exercises that you're running. So the first round of students for the cluster project, they start Monday, July 3rd, 10 a.m. is when the cluster room opens. We'll be there from 10 to 2 on Monday, July 3rd. I realize it's the day before a holiday, but I'm sure everybody here is going to be on campus. And I'll come in for that as well. So I'll see you Monday, July 3rd if you're going to be in one of those first groups. The first TA office hours are Monday, July 3rd, 3:30 to 5 p.m. So there you might find either myself or Jay or Karthik or one of the TAs. And you can either message us on Canvas if you want, either inboxing or discussion groups that we'll have for each class, or just email me and I'll make sure that you get the answer or direct you to who you need to talk to. All right? So that's